then let's briefly do a recap of the stuff that we went over yesterday. What did we discuss yesterday? Try to do it without looking at your notes.
Null hypothesis.
The null hypothesis, and what else goes along with the null hypothesis? The alternative hypothesis. In your own words, what is a null hypothesis?
It has to have equality in it, so it's say like my height is less than or equal to Sarah's height, and then you draw that by having the mean, because we're going to do an average, not a population proportion. So you have the mu, and you have like greater than or equal to, and then you put whatever height she is.
Awesome. So you touched on a couple of things there. You said that for the null hypothesis, we want to have some kind of equality sign. Equals to, less than or equal to, or greater than. You're completely correct about that. Then you also said that we're going to have either mu or p. So that means in our hypotheses, we're always going to have a population parameter, right? And the only ones that we're going to deal with in this class are the average and the proportion. So you're completely correct about that too. But let's say that your little niece or nephew came walking up to you and go, "Hey, Betsy, what's a hypothesis?" You would say?
It's something you assume to be true.
It's something that you assume to be true, right? An educated guess, per se. So if you had to narrow that down, what you assume to be true, and it categorize that as one of those two kinds of hypotheses, which one of them is it? Which one do you assume to be true? The null hypothesis, right? We're assuming that the null hypothesis is true. It's what we believe to be true. And the only way that we're going to accept that it's not true is if what? How would you accept that it's not true? Yeah, like there's something significant that says, nope, this is not true, right? Kind of like what I always said was, Chapel Hill's always going to be Duke. I'm just going to keep believing it until, whatever comes up. I keep getting those in there. I can start telling who the Duke fans are, right? Like, it's just like, right. But, that's like an example of a null hypothesis, right? Then, what's the alternative hypothesis? Or what is a alternative hypothesis? Again, your little niece or nephew comes walking up to you and goes, "Hey, what's an alternative hypothesis?" You're like, first off, get out of my book bag, right? Like, what are you doing in my book bag? Looking at my notes. But what's an alternative hypothesis? Duke beats Chapel Hill, right? It's the contradictory of the null, right? So let's talk about that, right? If I say that my null hypothesis is that Chapel Hill beats Duke, right? If that's my null hypothesis, what's the opposite of Duke
beats Chapel Hill?
Be really specific. It's not just Duke beats Chapel Hill.
Every time.
It's not more.
Chapel Hill doesn't beat Duke.
Chapel Hill doesn't beat Duke, right? So be more specific about that. If Chapel Hill doesn't beat Duke, right? I guess in this scenario it's a little bit silly, but either Duke beats Chapel Hill or
Chapel Hill doesn't beat Duke.
There's just a tie, right? There's some kind of tie, right?
So it doesn't guarantee that.
There has to be. Then you're talking about the points, right? All I'm trying to illustrate with that example is this: the contrary to something isn't only the opposite of it, right? So that's why whenever I talked about last class, I said, hey, you can think about it as the opposite. But keep in mind that that's not 100% correct, right? The contrary of that simply just means that, hey, if it's not this thing, it's everything other than this thing, right? Now, we did learn a vocabulary word for that whenever we were going over probability. If you're in event A, what's everything that's outside of event A called? The complement, right? So it's the complement. Good. So the complement of the null hypothesis is, generally speaking, the alternative hypothesis. All right, but the alternative hypothesis is simply just a thing that you don't believe is true, and you need convincing evidence to show you that it is true.
Is this so? This is kind of similar. This has something to do with probability, right? So say the Chapel Hill cannot beat Duke, or all these other possibilities, but there's usually like a finite amount, right?
That's right.
And not a very vast amount given the probability.
That's right. Usually speaking, right? once you get to the point where there's an infinite number of possibilities, that's getting into what's called asymptotic theory, right? And think about, what does an asymptote mean?
I don't know.
It's not necessarily. It keeps approaching, right? It's like two lines that keep approaching themselves, but they actually never touch. That's what you call an asymptote. So once you start having an infinite number of possibilities, that's what we call like asymptotic theory, because now we're like way off, like near infinity, if we want to start answering some of those questions. No, great question, but yes, it absolutely has to do with stuff with probability. And actually, every time that we're coming up with a confidence level, or most of the times that we're using numbers that are somewhere between 0 and 1, we're applying probability theory, right? So whenever we come up with our confidence level, we're essentially answering the question of what's the probability of something happening. And we're restricting that probability with restricting our alpha level. But let's get a little bit more into this stuff that's going to be important for you guys to answer the questions in this class. And one of the things that we need to start looking at are what's called our rejection regions. So the rejection regions are this. We have a hypothesis, and usually what we're going to try to do is we're going to focus either on our null or our alternative hypothesis. Whenever we answer questions, we're always going to answer these questions and provide interpretations in terms of the null. But one of the things that we're going to look at in order to determine our rejection regions is actually the alternative hypothesis. And what do I mean with that? Let's think of a scenario here real quick. And let's say that you're looking at somebody's blood pressure. Right? Somebody can have high blood pressure or somebody can have low blood pressure. Right? So then there's going to be a cutoff on one side that says if you're above here, you have high blood pressure. And then on the other end of the spectrum, there's going to be a cutoff that says if you're below here, you have low blood pressure. Right? Is everybody good with that? So we're still working with two cutoffs, and in between, we're going to say that's a healthy amount of blood pressure. That's the type of scenario that we've been working so far with in this class, where we had some distribution, and we're either going to say that it's a population distribution that's normally distributed, or that our sampling distribution is going to be approximately normally distributed. But what we've always been saying so far is that we have two cutoffs. And we've always been splitting our alpha level up into these cutoffs, right? So then if you said, hey, I'm going to take somebody's blood pressure, and I'm going to see where that blood pressure falls. Now, let's say that the blood pressure falls somewhere in between this area right here. We're going to say that this is a healthy blood pressure. But if somebody is too high or too low, right, too low or too high, right, we're going to say that those things are bad blood pressure. Now what we're going to start doing in Chapter 8 is we're going to start changing how we talk about it ever so slightly. And what we're going to say is this. I think you have healthy blood pressure. Now I'm phrasing this as a hypothesis. Right? Now, I think you have healthy blood pressure. I'm going to have two cutoffs where I'm going to know that above here, below there, you're going to have unhealthy blood pressure. Now I'm going to go and I'm going to take your blood pressure, and I'm going to see where you fall. If you fall somewhere in here, I'm going to say that my hypothesis that you have healthy blood pressure is correct. If, however, your blood pressure falls either over here or over here, I'm going to say that my hypothesis is incorrect and that you, in fact, do not have healthy blood pressure. That make sense so far? So then, if your blood pressure lands in this shaded area over here or this shaded area over here, I'm going to reject my hypothesis. And that's why we call those shaded regions rejection regions. Because if stuff falls in those shaded areas, I'm going to reject my hypothesis. Does that make sense? So we can definitely have scenarios where we have two cutoffs, kind of like blood pressure. Too high, no good. Too low, no good. Right? But you can also think about scenarios where you just have one cutoff. Right? What would be a scenario where you have one cutoff for something that's either on the low end or one cutoff for something that's on the high end? Scores? I heard two people talking, so I couldn't understand. What do you guys?
Left tail or right tail?
Yeah, left tail or right tail. So come up with an example where you just have one cutoff or something, and it's either in the left tail or on the right tail.
I said test scores.
For example?
So like an example, at 60 would be a fair score.
Cool, right? So you could say that, hey, if I want to pass this class, I need to be above a certain range. If I'm below a certain range, I fail this class, right? So that would be an example of something like this. So now, if you want to word this in terms of a hypothesis, you could say, I think you pass this class. That's a hypothesis, all right? Everybody see how I'm trying to phrase these things in terms of hypotheses now, right? So now, if your score is above this cutoff, my hypothesis is true, so I'm going to accept it. If, however, your score falls below some cutoff, now I'm going to reject the hypothesis that you passed this class, and therefore we're going to fall in the rejection region. You guys starting to see why we're calling them rejection regions? All right, what about an example where there's an upper end cutoff? What's an example where there's one cutoff but it's at the high end?
Could be if you got below the test score, do you fail? Or is that too much?
So yes, so you could say, hey, instead of my hypothesis being you passed this class, your hypothesis could be you failed this class, right? Now, if I say, hey, you failed this class, and then I go and look at your scores, if you had some really low score, my hypothesis would be correct. If, however, I look at your scores and you have a good score, well, then my hypothesis that you failed this class would be correct, right? So you could do that. You could have, for this one, is you were able to go on like a roller coaster ride, right? Below this height, you cannot go on the roller coaster ride. So I could say, hey, your height is sufficient to go on this roller coaster. You come up with a whole bunch of different examples, right? Everybody get the gist behind these?
Does this also apply to the not just the two possibilities? So say you passed or failed, but maybe you withdrew or dropped.
Yeah. So what we're only going to do in this class is we're only going to have our rejection regions in the tails, either in both tails or in just one tail. But yes, you can absolutely have rejection regions that are also within the middle of the distribution. What would be an example where you would have a cutoff in the middle of a distribution? It might be something like
Like a tide.
oh, what?
Maybe like you said, a tide or something.
A tide or something, or somewhere where you're just like, hey, high numbers are no good, low numbers are no good, and somewhere in between there's also some numbers that's not good, right? What would it be?
Could be like blood pressure, where your blood pressure's too low, it's not good, and where your blood pressure's too high, it's not good.
Yeah, but then in the middle there's a range where blood pressure isn't good either. I don't know about if that would be true, right? What would be a scenario where you had a cutoff in the middle?
It's hard to think of what.
Could be temperature.
How so?
Like you want it to be hotter in the winter, inside you want to be colder, and so the middle is not maybe a good thing.
Okay, maybe like if you're thinking about like plants or something like that, right? Like, yeah, maybe that's a good one, right? Like, where do I don't know then, like, but something along those lines. You guys get the gist, right? You're not going to see that kind of scenario in this class. We're only going to have rejection regions in the tails. I'll try to think of an example, but we don't need that for today's class. All right. So now the question becomes is, how do we determine our rejection regions? Our rejection regions are always going to start at these things right here. These are like your beginning portions of your rejection regions. And the vocabulary word that we're going to use for where our rejection regions begin is going to be the critical value, or if we have two rejection regions, then we're going to have more than one, so that we're going to have critical values. But the critical values are where our rejection regions begin. Now, these critical values, we're just assigning a new name to something that we've used a lot in the past. If you look at these distributions, and we're now looking at a cutoff. What have we used for these cutoffs in the past? Not our standard deviation. It might be a little bit clearer if we look down here at this picture, right? If you said, hey, over here I wanted to have alpha divided by 2 in it, and you said I want to figure out the cutoff where above here I have alpha divided by 2 of my graph, your z-score is just your critical value. Right? Is everybody good with that? So we've just been calling them z-scores. Now that we're dealing with hypothesis testing, we're just calling them critical values. Right? They're the exact same thing. But now let's draw a distinction. Here, our critical value is simply just our z-score. Right? But here, the way that we're going to determine this critical value is based off of alpha divided by 2. Because we're splitting up alpha equally into both those regions. That's what we did whenever we were doing confidence intervals. But now, if we only have one rejection region, we no longer are splitting alpha up into 2 regions. We're clumping all of alpha into just this one region. So therefore, whenever we look up the z-value, what we're not going to do now is we're not going to take alpha and then divide it by 2 and then go hunting for that percentage in our z-table. Instead, what we're going to do is we're just going to take alpha and then go straight to our table and look up that z-value because we're not splitting alpha up anymore. Right? Does that make sense? Right. So that's why in the past chapters, I always said, hey, let's talk about what alpha is first from our confidence level, and then we'll figure out alpha divided by 2. And back then I said that one of the reasons why I was doing that is because once we get to chapter 8, there's going to be scenarios in which we do not split up alpha anymore, and now we're at that point. All right. So the other thing that we're going to introduce is what's called the significance level of a test. Well, if you think back to our confidence level, right? Confidence level. What was the formula for our confidence level? What was the formula that we used to determine our confidence level? 1 minus? Yeah. And then you're drawing it out there with your hands. It's alpha, right? 1 minus alpha. That's how we always came up with our confidence level. And that's how we could always say, hey, if we had alpha, we could determine what our confidence level was, or vice versa, just like we did in the previous example. So here, this alpha, the thing that we're doing now is we're simply just assigning a new name to alpha. And alpha is what we're calling our level of significance, or simply just our significance level. So instead of referring it to alpha now, we're just giving it also a new name, and that's significance level. So now we know that the z values that we've been talking about, now we're going to start calling those critical values. And this alpha that we've been using, we're just going to sometimes also refer to that as the significance level. So those things are synonymous. All right. Now, this down here is going to start to become a little bit more important. And this is also going back to what I skipped on the previous page. Let's first talk about the easy thing about this. Whenever we have just one rejection region, we're going to call that a one-tailed test. If we put all of our alpha into one tail, so either here or here, we're going to call that a one-tailed test. Because we're only using one tail. If, however, we have two rejection regions, and therefore are splitting alpha up equally into those two rejection regions, well, what do you guys think this is called? A two-tailed test. It's a two-tailed test. Now, clearly, if we have a one-tailed test, we can either have our rejection region in the left tail, or we can have our rejection region in the right tail. So therefore, if we have a one-tailed test, we can either have a left-tailed test, which would be up here, or we can have a right-tailed test, which would be right there. I know this got a little bit convoluted up here, but I think it's a pretty simple concept to follow, right? Does anybody have any questions about what a one-tail or two-tail test is? left tail or right tail test? I think everybody's good on that. All right. That's the easy stuff. The little bit more difficult stuff is now this right here. It's a little bit more difficult, but also crucially important. And what that is saying is this. We're going to determine which one of these scenarios, which one of these three scenarios we're in, based off of our alternative hypothesis. So, one of the things that we're always going to do is we're going to say, okay, where are our rejection regions? And the way that we determine where our rejection regions are is always, always, always based off of the alternative hypothesis. Now, if our alternative hypothesis, right, and again, for our alternative hypothesis, we can only have one of three possible symbols, not equal to, strictly greater than, or strictly less than. Based off of which symbol we have in our alternative hypothesis is going to determine where our rejection regions are, right? So, here's a quick and easy way that I've come up with that will hopefully help you remember where our rejection regions are going to be for a certain problem. It's a little bit silly. It's kind of going along the same lines of is there Ebola in the classroom, but it really helps out. So first thing is this: if we want to figure out where our can you guys see that? Make sure that this thing is going. If we want to make sure. Or if we want to determine where our rejection regions are, we're always going to look at our alternative hypothesis. Suppose that we're looking at a mean, then right here we always wrote our population parameter. I'm going to use one of these symbols. Here I'll just go down with this one right here. It's strictly less than. And then what do we always have to the right of this? Some number, right? What's your favorite number? 23. Like Michael Jordan, who also played for the Tar Heels. Got it in there. All right, so this is usually how we would write our hypotheses, right? Now, the format of this, how we wrote these, is really, 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 really important. And this is not something that I mentioned yesterday. But if you look at all the examples that we came up with yesterday, they're all written almost exactly like this. The format of this is that we always have the parameter, then we have some math symbol, and then we have some number, right? So all of these is of the form a parameter, then the math symbol, and then we have some number as we go from left to right. That's important. Why is that important? Because now if you look at your hypothesis, your alternative hypothesis, you have this symbol here, and here it's strictly less than. If you simply just draw a horizontal line and make this into an arrow, it points to where your rejection region is, right? If you go down here and you say, hey, if our alternative hypothesis is strictly less than, which is the same symbol that we have right here, it says that you have a left tail test, and it's pointing towards the left. Right? Is everybody good with this? Let's do another one. Suppose your alternative hypothesis was parameter, symbol, math number. How are you going to determine where your rejection region is? Just make this thing into an arrow. Which way is that arrow pointing? To the right. So now you're going to have one rejection region on the right. Does that make sense? Now the only one that we haven't talked about yet is this. Suppose that your alternative hypothesis is again parameter, math symbol. The only one that we haven't talked about yet is not equal to, and number. Can you draw a horizontal line and make this thing into an arrow? Nope, you can't do it. So therefore, we're going to have two rejection regions. Does that make sense? So if you can draw a horizontal line and make it into an arrow, that arrow is going to point to where you have your rejection region. If you cannot draw a horizontal line and make it into an arrow, then we're simply just going to have two rejection regions. That's the quick and easy way to remember where your rejection region is going to be. Is everybody good with that? All right. Now, if we go back to the portion that I skipped at the beginning of last class. Right? If you guys remember, I said, hey, I'm going to skip all this, and I put a bracket around it, and I say it's not going to make a whole lot of sense until we practice a little bit more. Well, this is essentially just saying what we did before. We're looking at the alternative hypothesis. If it has this form, we're going to reject our null hypothesis based off of these characteristics. All right. Now let's get into some numerical stuff. Unfortunately, the next 3 pages are kind of like definition stuff. I'm going to go through these definitions rather quickly because we just need to focus on a couple of things, and then we're going to do some numerical examples. So if these next couple of things aren't super clear to you as I'm going over them, don't worry about it. Once we get to the examples, that's the important part. All right. So here's this. What we've talked about so far is we've talked about a hypothesis, coming up with some statement. Based off of that statement now, we can figure out where our rejection region is, right? And now what we're going to say is this. The next step after that always was, like earlier when we talked about, I said, hey, I think you have good blood pressure, hypothesis. Now from that we can determine how many rejection regions that we have. The next step after that was what? I said, hey, I think you have healthy blood pressure. What's the next step?
Test your blood pressure.
Now I'm going to test your blood pressure, right? So now I'm going to test your blood pressure, and I'm going to see where on here you fell in order to determine whether I'm going to reject my hypothesis or not. That, where I'm seeing where you fall, we're using that to test my hypothesis. So that's what we're going to call a test statistic. Right? We're using that value to check my hypothesis. So that's what we're going to call a test statistic. Now, why is it a statistic? Where do we get statistics from? Samples. A statistic is a number that we're calculating out from a sample. So when I say, hey, I'm going to test your blood pressure, I'm taking you as a sample. So I'm taking you as a sample, I'm calculating out some number from it, that's a statistic. I'm using that statistic to test my hypothesis, so therefore we're talking about a test statistic. All right, cool. So we're talking about test statistics here. And I'm going to try to put these next 2 pages side by side. Can't really do them side by side, so this will work out just fine. If we look at these test statistics, what we essentially have is we have 1, 2, 3, 4 test statistics, right? Which kind of sucks. But let's take a look at these here for a second. What's the only difference between the first one and the second one? Standard deviation. One of them has sigma and the other one has S, right? So what's the difference between these two down here? T and a Z, right? So just based off of that, where do you guys think we're going to use these? These right here are going to be for large samples whenever we know sigma or we don't know sigma. But essentially it's the same formula. We're always just going to put the standard deviation right here, right? When are we going to use Z versus T down here? Small sample or large sample, right? Is everybody good with that? It's the exact same thing though. The only thing that's changing now is whether or not we know sigma or S. And now we're just going to put a large n right here and a small n right here for T's and Z's, right? Now, the good thing about this is you don't have to memorize these formulas because if you go to your formula sheet, on your formula sheet, we have this column right here on your formula sheet. So if you guys know how to use this portion of the table, which I'm assuming that you do after chapter 7, right? Knowing that here we have a sample size greater than n, here we have a sample size larger than n, or to determine whether or not we know a sigma or we don't know sigma, determine which confidence interval formula that we needed to use. If you're good with figuring out which confidence interval formula you needed to use, then you should also be good with determining which test statistic formula that you need to use. Right? The test statistic formula that you need to use is simply just figuring out where on this distribution we fall. Another way of saying that is if your test statistic falls right here, what are you going to do? Your test statistic falls right there. What do? You do not reject the hypothesis, right? Because your test statistic would have to fall, say, in here in order for you to reject your hypothesis. Right? Is everybody good with that? Now, the last question I'm going to ask you guys then before we go on and do some numerical examples is this. I said, hey, if your test statistic falls right here, what do? And you said, you do not reject the hypothesis. Which hypothesis?
The null.
It's always about the null, right? Always, always, always about the null. We either reject or we do not reject the null hypothesis. Good question, right? So the question is, if we reject the null hypothesis, does that mean that we're going to accept the alternative hypothesis? And the answer to that is no, not necessarily. Right? Why that's the case is a little bit more theoretical, but we can work through it in terms of like an example. Right? Let's say that let's go to a football game instead of a basketball game. And the reason why I want to go to a football game instead of a basketball game is because football games can have tied scores, right? That's the main difference between those. So in a football game, you can either have one side wins, the other side wins, or they're tied scores. Suppose that we came up with the example. Anybody in here a Chicago Bears fan? All right, I'll row down the river by myself. Suppose that we had an example where the Bears played the Packers. And we all should know that the Packers are a terrible football team. Now, if we look at the scores, right, suppose I came up with a hypothesis that said that the Bears were equal to the Packers. I'm going to hypothesize that the Bears are going to tie the Packers. That's my hypothesis. The alternative that I'm going to come up with is that the Bears are going to lose to the Packers. All right, is everybody good with this? Is this an okay hypothesis to have? Why not? Yes, but my question was just, is this an okay hypothesis to have? Yes. And that is okay. We have some kind of equality sign right here. We have something that does not have equality right here. So we're meeting all of our standards, right? But what you just highlighted is exactly the point that I'm trying to make. Here there is a possibility where both of these things are wrong if the Bears beat the Packers. Okay. So just because we arrive at the fact that the null hypothesis is wrong doesn't mean the alternative is right. Okay. Exactly the point. So it doesn't mean that the alternative hypothesis is right. So therefore, all that we ever say is we always just talk about the null hypothesis and whether or not we reject or do not reject the null hypothesis. We're never making a judgment on whether the alternative is actually correct. That make sense? Cool. Yeah, that's a great question. Any other questions about any of this stuff before we go on into numerical type examples? You guys get the gist of the stuff that we're doing? All right, then let's do some examples. This stuff right here, I'm just going to point this out in like 5 seconds. This is the step-by-step guide for how your textbook or the textbook that accompanies this course tells you to do hypothesis testing questions. My process is a little bit different than that of the textbook, but it's in the textbook, so I included it in the notes. So if you guys prefer that one, you can use that one, but I'm going to show you guys something else. All right, so let's go to basic hypothesis testing questions. First off, it says the recipe of a bakery item is designed to result in a product that contains 8 grams of fat per serving. The quality control department samples the product periodically to ensure that the process is working as designed. Suppose that it is known that the population is normally distributed with a standard deviation of 0.15 grams. A sample of size 5 is taken with a mean of 7.65 grams. Construct a rejection region for a choice of alpha of 0.1 and interpret your results. All right. There's clearly a lot of stuff that's starting to come together in Chapter 8, right? Which is why I said, like, after the second test, like, if you're struggling with, like, Z values and stuff like that, like, stuff is going to start spiraling. So what I'm still going to say is, if you guys have questions, make sure you ask those questions. I'll definitely answer it to the best of my ability. So let's first start off with this. What's always the first question that I've asked you guys whenever we do problems in this class? No, not quite. Like even when we were back in Chapter 2. Chapter 3. Not the Z value. Right, in Chapter... population or sample. And it's always trying to help you guys out when you're on a test. Whenever you're taking a test. Find the keywords, right? How do we know this is a Chapter 8 question, right? So, how do we know that this is a Chapter 8 question? There's a rejection region, right? We know that rejection region is definitely part of hypothesis testing, so that's one of the buzzwords that we can use for Chapter 8. All right, so what we're going to do now is, you can disregard this right here. I haven't really talked about this yet, but we'll get back to that here in a second. The first thing that we're going to always do whenever we do any kind of hypothesis testing is we're always going to write down our null and our alternative hypothesis. That's why we spent so much time on it last class. All right. Whenever we're trying to write down our null and our alternative hypothesis, we always ask ourselves 3 questions. What was the first question that we always ask ourselves? Is there a statement which contains equality? Here in this problem, is there a statement which contains equality? Contains 8 grams of fat. So here we want to have a pastry that has 8 grams of fat in it, right? What symbol is that? Equals to, so therefore it becomes our null hypothesis. So in our null hypothesis, we're going to have something that says equal to 8 grams. What's the second question that we ask ourselves? Is there a statement which does not contain equality? And do we have such a statement up here? I heard both answers. If you think there is one, what do you think it is? Here, with a mean of 7.65 grams. All right. So, I heard somebody say no. Why do you think that this is not a statement about inequality? It's saying what the mean is. I didn't hear what you said. Doesn't say that it's less than, but Josh is saying that it's less than 8 grams, so it is saying less than. You kind of had your hand up?
So your alternative always has to be the same number of that, right?
Your alternative always, the null and the alternative always has to have the same number, yep. But what is this 7.65 grams talking about? The sample, right? What do our hypotheses always talk about? The population. So does this pertain to our hypothesis? No, this only pertains to the sample. So this doesn't tell us about something that does not contain equality. So let me ask you guys the question again. Do we have a statement which does not contain equality? Cool. No, we do not. So we do not have one, so therefore our alternative hypothesis becomes what?
Not equal.
not equal to, right? It's the complement of, or like I kept saying but pointed out a little bit more clearly today, you can think of it as the opposite, but now we know more specifically that it's the complement. All right, everybody good with this so far? Third question is, what's our parameter of interest? Mu, because we're dealing with averages and not with proportions. It's either mu or p in this class, so here we have mu. All right, so here we have our null and alternative hypothesis. Everybody good with this? All right. The next step that we're going to do that I'm going to try to encourage you guys to do for this, so I'm going to call this right here step number 1. Step number 2, I'm going to continue to encourage you to draw a picture. One of the things that we're going to say here, and I believe it even says it here in this problem, that the population is normally distributed. Here, third line to the fourth line. So therefore we know that we're going to have our normal distribution or our bell-shaped and symmetric curve. The next thing that we want to do now is we want to start to identify where our rejection regions are. Whenever we try to determine where our rejection regions are, what are we looking at? It's not. So I heard a couple different answers. Whenever you want to point to it.
Could it be the symbol?
You look at the alternative hypothesis, right? You look at the symbol of the alternative hypothesis, right? And what did we do to the symbol to try to determine where the rejection region was? Yeah, we try to like turn it into an arrow to see which way the arrow points, right? Can we turn this one into an arrow?
No.
So how many rejection regions do we have? 2. Cool. So that's going to be part of our second step, is determining where our rejection regions are. And here we first determine that we have 2 rejection regions. Whenever we're trying to determine where our rejection regions are, we always look at the symbol of the alternative hypothesis. Right? Is everybody good with that? All right. Now, why is that so important? Well, we have 2 rejection regions. But now we also know that we're going to split alpha up into 2 areas. So over here we're going to have alpha divided by 2, and over here we're going to have alpha divided by 2. So just like we did in chapter 7, in this problem, how big is alpha?
Alpha is here.
Good, because it literally tells you in this problem that alpha is equal to 0.1, right? So it doesn't give us a confidence level, but even if we had a confidence level, we could figure out alpha. But now we could also call alpha what? We learned a new vocabulary word for alpha. Significance level. So we're also going to see a problem here in a little bit that says our choice of significance level is equal to 0.1. And we know that those 2 things are synonymous. Right? All right. So now we know that alpha is 0.1, so therefore alpha divided by 2 is 0.05. So therefore now we know that our cutoffs right here, which we're calling our what? So this shaded area is our rejection region. But what signifies the beginning of the rejection region? Our critical values. So here we're going to have 2 critical values. Something that I just realized I forgot to point out to you guys is that in math and in stats, whenever we're trying to distinguish 2 things, we hate having the same symbol for 2 things. So therefore what we're going to do is we're going to call this one right here capital C, and this one over here on the right we're going to call it capital C with like a little apostrophe or a prime, yeah. This is the notation that your textbook uses. Other textbooks sometimes call this one number 1 and number 2, but I'm not going to use that one here. We just somehow try to distinguish these 2 things. So the one on the left, if we have one that's on the left for the left tail, we're always going to call that one C. If we have a critical value for the right tail, the one on the right tail, we're always going to call C prime. So it's not like the first one is C and then the second one is C prime. That's not how we're going to do it. The one on the left is always C. The one on the right is always C. All right. Everybody good with that? So we know we have 2 critical values. Now the next thing that we really need to try to identify is what are these critical values? What are the critical values? So how do we figure out what these critical values are? Well, the method that we're going to try to use in this for this example is we're going to try to convert everything to the units of the problem. So here what we're saying is that our hypothesis is that these pastries have 8 grams of fat. What we're now going to try to do is we're going to try to figure out cutoffs above which or below which we say that our hypothesis is incorrect. Right? Think about it like this. I am saying that these pastries have 8 grams of fat in them. If you go out and you test it and it has 7.9999 grams of fat in it, are you going to call me a big fat liar? No, right? Like that's pretty darn close, right? So we're trying to figure out what is our cutoff though. If it only has 7.99 grams of fat, are you going to call me a liar? 7.9 grams of fat? What about 7.5 grams of fat, right? You guys get the gist? We're trying to find the cutoffs, yeah.
I was confused. The 7.65, is that not the middle? Because it says 8. You put 8. So why isn't that?
Good question. So that's usually something I don't talk about until like the next class, right? But you picked up on it, so let's talk about it here. No, that's a great observation. Because what we're doing now is we're doing something a little bit different than what we did for confidence intervals. Because you're right. In confidence intervals, what we did was, in confidence intervals, we always started off with our point estimate, right? And that's when when we first started talking about confidence intervals, I kind of drew it up there like that. And then we always added something to this point estimate and subtracted something from this point estimate. We said that these things were a margin of error. So therefore, we always had our confidence intervals centered on our sample mean, right? And you're saying, hey, wait a second, 7.65, that's our sample mean, so why aren't we centering this on 7.65? That's a great question. The reason is this. I'm coming up with a hypothesis. And if I'm too far off of my hypothesis, I'm going to say my hypothesis is wrong. What I'm going to eventually do is I'm going to take a sample, and I'm going to use that sample to say, hey, am I close or am I far from my hypothesis? So what we're going to use that 7.65 number is we're going to use that 7.65 number to see if we're right here or if we're right here. So therefore, now we're no longer centering things on our sample average. We're centering things on our hypothesized value, and we're using our sample average to determine if we're going to accept or reject. Right? It's a really good observation. All right. All right, so what we want to do is we want to find out where our rejection regions begin, but we want to determine these in terms of grams of fat, which is just the units of this problem. Because what we could do is this, and this is the first step that we're going to use in this process. I want to figure out what these z values are first, right? So you guys should be able to do this. Take like 30 seconds for yourself and see if you can find out the z value for these critical values. What z value do you guys get? Good. So we're saying then for our alpha divided by 2 of 0.05, this one over here should be 1.645, and this one over here should be negative 1.645. Is everybody good with that? All right. So, and this is what I mean with converting everything to the units of the problem. If I come to you and I say, hey, I think that the average grams of fat in these pastries are 8 grams of fat. But if you take a sample and you're below a z value of negative 1.645, you can reject my hypothesis. That doesn't really say a whole lot of stuff. Right? Like if you go out and you take a sample of stuff. You don't want to know it in terms of a z-value. You want to know it in terms of grams, right? So now what we're going to do is we're going to take these z-values and we're going to convert them to grams of fat, right? Does that make sense? All right. You have a z-value, and you're trying to convert this to grams of fat, right? Or just to an x. How do you do that? If you had an x and you want to convert that to a z-value, what do you do? Good, right? So if you had an x value and you want to convert that to a z-value, we would just use our z-value formula of x minus mu over sigma. So we're going to boil it back down to this equation again. This mu now is what? Good. That mu is this thing right here, this 8. And another way of saying this 8 is this is just our hypothesized value, right? That's our hypothesized value. So we're going to start calling this thing now mu naught for our hypothesized value. And this sigma now, we're going to use this as sigma divided by the square root of n because we're taking a sample to figure these things out. We're essentially working with a sampling distribution. So another way of writing this is this. You can say that we're going to use, for the left-hand side critical value, we're going to have mu sub naught minus z sub alpha divided by 2 times sigma divided by the square root of n. And over here, we're going to have the right-hand side critical value of mu naught plus z sub alpha divided by 2 times sigma divided by the square root of n. Say again? Thank you. I kind of jumped the gun here on something.
Where did the x go?
And the thing that I jumped the gun on is this. How do we know that we're using z's? Because what? We know the population standard deviation. And what else? The thing that I forgot to do is I forgot to ask those two questions of is n greater than or equal to 30 and is sigma known. These two things determine whether or not we're going to use z-values. So I should have this right here as my third step, and this right here is my fourth step. Now, do we have a sample size that's greater than 30? No. What's our sample size here? Do we know our population standard deviation sigma? Yes. So since we answered yes to one of those questions, now we can use these. So I should have asked you guys these two questions first before we looked up these z-values and before we jumped down here to these two equations. All right. But now that we're down here to these two equations, we can start plugging values into this formula. We know that our hypothesized value is 8. We looked up our z-values of 1.645. What is sigma equal to in this problem? 0.15. And our n, we already said, was equal to 5. Is everybody good with what we're trying to do here in step 4? Yes?
If the c is negative, well, that's how we cannot make it negative in that problem? Or you were still just going to keep them positive?
Good question. I think you're asking when we put it in right here?
Mm-hmm.
Good. So you can think of this formula as mu plus this right here, right? Plugging in that plus right there. And then what you can think of, I'm not going to teach it to you guys this way, but this is one way because I think this is the way that your mind is going. You can think of this as being a plus, and then when you plug this one in, it's going to be a negative right here. and when you plug this one in, it's going to be a positive right here, right? Remember that in chapter 7, what we always said was that we're going to use the z sub alpha divided by 2. We always just use it as a positive value, right? So that's the process that I'm following along with. So that when you look up these z values, we're still just going to use the positive value of it. So then that's why I'm using this formula right here. So if you want to think about it as in terms of plugging in a negative value right here, then you can just remember that both of these equations are going to be positive. Does that make sense? Cool. Awesome. Great. Any other questions about this so far? You guys are asking great questions.
Could I write it as 8 plus or minus 1.625 and do it that way?
Great question. When would you not be able to do that? Good. When you only have one rejection. Because then we're not adding and subtracting to find out both of these. We would either be adding or we would be subtracting if we only had a one-tailed test. Does that make sense? Cool. Yep, great question. Great question. Any other questions about this stuff? All right. If we do this arithmetic, we're going to come up with this value being 7.89 and this one over here being 8.11. So what did we just find out? We found out that our left-hand side rejection region begins at a value of 7.89 and below. And we find our right-hand side critical value to begin at 8.11 and above. Right? Everybody good with this so far? Now, Cherise, what's our next step going to be? What's our next step going to be? The question you asked earlier? Cool. So what's the mean? Good, 7.65. You're close. What we're saying here is this, right? We're saying that I think that there's 8 grams of fat in these pastries. And you're saying, that sounds reasonable. Let me go out and let me test these pastries. You go out and you test the pastries, and the pastries that you come back with, the sample average is 7.65 grams of fat, right? But we just said that, hey, my rejection regions begin at 7.89 or 8.11. So where does 7.65 fall? Left-hand side, right? So 7.65 is going to be below here. So that's where we compare now the 7.65 from. The 7.65 is going to be below 7.89. So therefore, we're going to be inside the rejection region. And therefore, we're going to reject the null hypothesis. Good. So what I'm going to do is I'm going to break that down into 2 steps. I'm going to say that step number 5 is to look at our sample average. And here in this problem, our sample average is 7.65. And then step number 6 is going to be to compare our sample average of 7.65 to our 2 critical values. And we're going to say that 7.89, which is equal to our left-hand side critical value. I shouldn't write that. I should say that our x bar, which is equal to 7.65, is less than 7.89, which is equal to our left-hand side critical value. That's how I should write it. Does it matter that I only mentioned C up here and not C prime?
No.
Why does that not matter?
Because you're falling into the one rejection
Region, right? Yeah. I'm falling into this one over here. So if I'm to the left of this cutoff, well, I don't need to mention this one at all. Right? Does that make sense? So all I really need to say is that here I'm going to be to the left of this, and 7.65 is less than 7.89. So x bar is less than C. It's just to name the fact that we're inside our rejection region. You guys now see why it's so important that we call this one C and we call this one C prime? Because if I said that this was C prime, That's not telling me a whole lot. Being less than C prime doesn't tell me anything, right? It could fall in here or it could fall over here. All right. So then we do this. So therefore we reject the null hypothesis, since we're always rejecting the null hypothesis, that mu is equal to 8 grams. So if I write a since in front of all this, since this is the case, we reject our null hypothesis, you can think of number 6 as being an interpretation. All right. So that was a rather long example. One of the things that I want to do is I want to summarize what we did, show what we did that's different from chapter 8 than it was what we did in chapter 7, and then we'll get on to it. So, did we do this in chapter 7? No. So writing down our null hypothesis is something new, but you guys feel confident about null hypothesis. Did we draw pictures in chapter 7?
Yes.
Yeah. Like, unfortunately it wasn't like Mickey Mouse or anything like that. But we definitely did this portion over here. Did we ask these 2 questions in chapter 7?
Yeah.
Yep. Did we find out endpoints in chapter 7? Yep, we definitely did this in chapter 7. And did we compare, what is this thing called again? That's our test statistic. Did we have a test statistic in chapter 7? Nope, we didn't have a test statistic because we had nothing to test in chapter 7, right? Now we have a hypothesis and we're trying to test that, but we also had an interpretation. So really, the main 2 differences between what we're doing in chapter 7 and what we're doing in chapter 8 is we're starting everything off with a hypothesis, and then we're comparing a test statistic to a hypothesis.
So when we have the mean given of like 7.65, and you don't have to go through and find the test statistic, it's automatically our test statistic?
Yes. So if you're given a sample mean, that sample mean is going to be your test statistic. What we're going to do starting on Thursday is, instead of leaving everything in terms of grams of fat, we're going to start to convert things to Z values. And, well, we're still going to use the 7.65 number. We're just going to change it to a Z value and then compare Z values to Z values. Cool. Yep. All right. I'll see you guys tomorrow.